Good morning. Can you all hear me? All right. Good morning. Can you all hear me? Uh-oh. Can you hear me? Okay, all right, I got a response. I just want to make sure you can hear me, otherwise I'll be lecturing and no one can hear anything. Okay. So today, I want to talk about the DC circuit analysis lab.
So currently I'm manipulating a bunch of data in CSV files and kind of mutating them so they can actually...
You got an open mic, Aaron.
Is what I work in.
Oh, sorry.
Right. Thank you. So we're going to do the DC circuits lab. And I'm going to talk about the motor lab, although I'm going to say a little bit more about the motor lab when we talk about it in the lecture. But I do want to get you started on it because it's a project. Okay, so I want to get you started on both. This will be due on the 11/5. And this will be due December 3rd. Before I get started, do you have any questions on the Ohm's Law Lab?
Yes.
Oh, go ahead.
Okay, I am struggling a little bit with interpreting my multimeter's readings. So for instance, what's the resistor supposed to be? 820. When I measure the resistance on the 820 ohms resistor, it tells me that the resistance is 0.820 ohms. Is that expected?
Is it on the kilo ohm scale? Is it on a 2 kilo ohm scale?
No, it's, yeah, when I set it to 2.
Yeah, so that's 0.82 kilo ohms.
Okay.
Right, because the maximum on the scale is 2 kilo ohms when you set it to that scale. So
sure.
If it reads 0.82, that's 0.82 kilo ohms. So it's still 820 ohms.
And then, so when let me grab it to look at the numbers. When I'm measuring the light bulb on the, I guess I would measure it on 200, I'm getting readings like 0.75.
I'm sorry, for the light bulb you said?
Yeah, so would I interpret that as 75 ohms?
What scale is it on?
I think it's when I have it set to 200. I can do it again real quick. I have the things near me.
Because then if it says 0.75, then it's 0.75 ohms.
When it's set to 200?
Yeah.
Is there something in the manual that explains this?
The manual is okay. I mean, yeah, I think one is, and maybe I didn't spend enough time discussing the values on there. So if the scale says 200, this means it reads from 0 to 200 ohms. If the scale says 2K, then it's reading from 0 to 2,000 ohms. Okay? So on any of those scales, the lowest is 0, but the highest is whatever that value is on that knob.
Okay. So yeah, when I have it set to 200, I'm getting a reading right now of about 1. So that would just be my...
Yeah, so that's an ohm then. That's the only one that's not in kilo ohms.
Okay. Yeah, thank you. I saw some other students. I was talking to some other people helping them out last night, and yeah, our resistances were just wildly different for the bulbs, and mine seemed to be the outlier. So,
Okay. They do, they're not going to be, they're going to vary based on from previous
yeah,
labs.
but I mean, mine was off by 1,000% from what they had. So
Yeah, maybe not that much, but that's that you're right. But that was probably because of the how you read
yeah.
the value. Other questions?
Professor, I have a question. What room are you going to be in today for the lab help?
So, like right now, I'm in 105C, but when I'm in between classes, I'm either going to be in 105C or my office. My office is 107A. You know where Tyler's office is?
I don't think I've been to Tyler's office yet, but
Yeah, I don't know how many of you folks have had a class on campus since, I mean, because we've been in the online mode for at least three semesters. So
yeah.
actually, this is the fourth semester. Anyway, so I'm in S107A. So if you walk into Sewell, where you face the polar bears, then I'm all the way on the left end of the hallway.
Okay, gotcha. Thank you.
Okay.
So you said 107A. Okay.
Okay, yeah. So it's either that or 105C. Because that's when I'm lecturing, like right now I'm in 105C. So I'm going between, I'll be going in between rooms.
Okay, thank you.
Okay. Other questions? Yeah, and I apologize, I wasn't clear on the scales on the multimeter. I think I just ran out of time. Okay, so if you don't have any more questions, I'm going to talk about the DC circuit lab. Tyler doesn't have a video for this lab. I'm hoping you watched the video for the Ohm's Law lab because he went through all the equipment. This lab, we're going to analyze the circuit I discussed in class. Let me check the chat real quick. Oh, I'm sorry, I didn't miss your question. If you need alligator clips, just work on the lab here. Okay? And then you can borrow our alligator. You can just work in the lab with the alligator clips. We won't let you take them home, but you can just sit in the lab and use them in the lab. Okay? Our lab also will be open. I'll have this room open too. Okay, and if that's a problem, I'll put you in if I know Harris has a class today, so if there's people in there, if there's a class in there or whatever, I'll put you in a different room, but that lab will be open. No, the lab won't be open on the weekend. Just if you can come here. So if you can come here around 11, although I have a class at 11, Tyler's here, talk to him. Maybe he can arrange something for you, okay, Isaiah? All right. So we talked about the circuit the other day. I drew it differently in the lab, actually. So you're going to build this circuit, and I want to show you what it looks like, or what it might look like on the board. Okay, I actually put the actual resistors. So this is what the circuit will probably look like on the board. So I'll leave it here for a second so that if you want to watch the video later on, you can. No, the board is different, and I like using this board because I taped the connector of the power supply here. So all I have to do is plug in the power supply here, and that's it. I'm all set to go. And I also have these two wires sticking out because this would be for connecting the ammeter for the second part. Okay? So this is essentially the circuit. It's pretty straightforward. So you're going to build that circuit and you're going to make a bunch of measurements. So in part one, you're going to stick a multimeter here, an ammeter, and you're going to measure the current here. Now, I'll leave it up to you whether or not you want to leave this meter in or not. And if you should tell me if you took this meter out when you made the other measurements. In part two, you're going to have to take this out, okay? Because otherwise you don't have enough meters to do the measurements. But in part one, I'll leave it up to you if you want to leave that meter in the whole time or not. But if you take it out, then you'll notice an effect on your results. Okay, when you calculate the difference between the theoretical value of the current through this and the measured value. Okay, so you'll set this up, you'll measure this current, and I'll leave it up to you to leave this in or not, but let me know in the when you write the lab report whether you took it out or not when you made the other measurements. You're going to measure the values of the resistor. The values of the resistor are listed on the lab. You have to use those values. You cannot use any other values, okay? Because that's what's provided in the lab kit. And so what you got to measure is, actually before you put it in the circuit, you got to measure the values of the resistor, okay? So before putting the circuit together, measure these values. Then once you have this circuit put together, you measure this current, we'll call I sub S. And you'll measure the voltage across the first resistor. You'll measure the voltage across the second resistor, the third one, the fourth one. And you'll measure the power supply voltage. Once you know those values, then you can calculate the current through each one of these resistors. Because the current through each one of these resistors, for example, the current through resistor 1 is just going to be that. Okay, the current through resistor 2 is going to be that. So you're going to calculate these values. You're going to calculate this value, etc. And then along with the uncertainties, we'll hold off on how to calculate the uncertainties. Okay, we'll get to that. And you know that in Kirchhoff's current rule, the current splits up here into two parts, I1 and I2. This current is I1 plus I2. And so your goal is to see whether the sum of these two equals what you measured within experimental uncertainty. That's why I want you to calculate I sub S along with this uncertainty. Okay. Similarly, you're going to calculate this current and this current. And the sum of those two is going to be the same current. In fact, in this particular case, I1 and I3 will be the same because all the current is going to go this way. And then this current is going to go this way, so I2 and I4 are going to be the same. Questions on that? The procedure is pretty clear.
And we would just solve that using the Kirchhoff's law with 2 loops?
Oh, I mean, I'm not even having you solve the circuit.
Oh, okay.
You actually don't need Kirchhoff's law just because if you want to solve for I sub s in terms of the resistors, I mean, these two are in series and these two are in series, and the combination's in parallel. So you can just use series parallel to solve that. It would be way faster to do it that way than using Kirchhoff's laws. Yeah, and you're right. If you were going to apply Kirchhoff's laws, because you have two independent currents, you'd have to use two loops. Okay. Other questions? All right. So that's part one. The purpose of this lab, well, there's two purposes. Again, learning how to make measurements in a circuit, building circuits, and verifying Kirchhoff's laws. So you will do all these calculations, and then these two are to verify the fact that their values is equal to the measured value. Okay? Your goal is to see if, to verify the current rule, does this value that you measure match these two values? Well, I shouldn't say match, but do the values overlap? Okay, do they agree? When I say they agree, do their values overlap, right? Because when you measure I sub s, you're not really measuring a number, you're measuring a range of values. Even this, you're not measuring a single number, but you're measuring a range of values, you know, in terms, because this instrument that you're using is not 100% accurate. Okay. Now in parts 2 and 3, or in part 2, there's really two parts to it, although they're the same. In part 2, what you're going to do is you're going to put an ammeter between points A and C in the circuit. So now you've tied these 2 points together. And this is not a balanced bridge, so you're going to have current going through the ammeter. Okay, I purposely chose the resistor values so that you will have current going through the ammeter. And I chose them this semester so that you have a fairly significant amount of current as compared to the total current. Okay, so again, what you're going to do is you're going to measure this current. You're going to measure this current. You already know the resistor values. And so the voltages will change. And so you got to measure this voltage, this voltage, this voltage, and this voltage again. Okay? So you're going to measure the voltage across the resistors. And then you have to calculate all the currents. And I don't know if I have enough space to write here everything you need to write. So you're going to measure all these along with their uncertainties. Okay? I'm sorry, you're going to measure all these and then calculate the uncertainties. And what you want to do is in table 2, when you collect the data in table 2, you want the setting of this meter to be on the highest current scale. Okay? You want the setting of this meter to be on the highest current scale because that's going to have the lowest resistance, and I want you to see the effect of the resistance on the circuit. Now, when this guy you're going to have to take out because once you measure this, then you're also got to measure these values. You would need a third ammeter, a third multimeter. You don't have 3, you only have 2. So for this part, you're going to have to actually measure I sub s and then take it out. Okay. So in table 2, you want this to be the highest meter setting, the highest current setting. Okay, so the resistance is the lowest. Of course, when you have it on the highest current setting, the number of significant figures decreases. That's a problem. Okay, so there's a trade-off between the current setting, the resistor value you have, and the number of sig figs you're going to get in your result. And this one you want to just keep. You want to keep this one on the lowest setting you can use. Of course, the lower the setting, the higher the resistance of this. Okay. Generally, I think this, and I'll tell you right. I think generally the setting for this will probably be in the milliamps, the 200 milliamp scale. I think, but you need to double check. You always start on the highest scale and see if you can go down. Then for table 3, you're going to make the same measurements, except that you're going to change this to to a lower scale reading. Either the 200 milliamps or the the 200 milliamp or the 20 milliamp scale. And so now the resistance will be higher. How does that affect everything? So that's another thing I want you to look at, is the effect of the meter in your circuit. It does have an effect, and you'll see it there. The one thing we're not doing in this lab is looking at the effect of the ammeter, of the voltmeter resistance. Okay, we're not looking at that, but that's something to consider too in your measurements. Okay. Let me see if, okay.
I do have a question real quick. The bottom left corner of the board is a little blurry. Can you just read out those values that I'm supposed to measure and calculate?
I1, so you need to measure R1, the voltage across R1, the voltage across R2, the voltage across R3, the voltage across R4, the current from the battery, I sub S, and the current through the meter that's between A and C.
Okay.
Okay? And then you have to calculate I1, I2, I3, I4, and then IAC. Now, what is IAC? Let me just say what IAC is. When you have this set up, if this is I1 and this is I3, this current is going to be I1 minus I3. Okay.
Mm-hmm.
So that's how you'll calculate IC, and you want to compare it to the measured value. And of course, you're going to calculate the uncertainty in this. I might have to rewrite this so I can get more. I ran out of space. Sorry. And then IAC. How do we write it in terms of this current and this current? Hold on a second. I think I have my resistors mixed up. Yeah, this should be. Okay, that's better. IAC then is going to be this minus that. From Kirchhoff's current rule. So in this part, you're going to verify Kirchhoff's current rule twice. Once up here, and then one here, and then once here. Actually, 3 times. Okay, so you're going to see if the sum of these two currents equals this, the difference between these two currents equals IAC. And of course, you're calculating this, but you also got to calculate the uncertainties. How are we going to find the uncertainties in these values, all of these values. Well, your multimeter should have a manual that comes with it. Okay, and the multimeter tells you the accuracy, but it's written in a funny way. Okay, so it'll say something like, let's say you're measuring a resistance. And let's say on the 0 to, I'm going to use a different multimeter. 0 to 1,000 ohm scale. Accuracy is, this accuracy means what it means is the uncertainty due to systematic errors and the uncertainty due to random errors. Then when the engineers designed this, they took them both into account. Okay, normally when we make measurements, we only are concerned of random errors, but they're including random and systematic errors. Anyway, let's say it's 1% plus or minus, plus 5 digits. This one represents the least significant figure. So let's say you got a value of 250.3 ohms. Okay, let's say you measured this. The meter gave you this value. The manual is telling you that that last digit can be off by 5. This tells you how far off the least significant figure is. So the least significant figure is off by 0.5. Okay? Now, we take the 250.3 and multiply by 1%. And this gives you an uncertainty of 2.5 ohms. So this has an uncertainty of 2.5 ohms plus 0.5. And so my uncertainty is 3 ohms. And so if I'm going to report this value correctly, I should say R is 2.50 plus or minus 0.03 times 10 to the second ohms. Or I can write it as Does that make sense?
Yeah, it does. This
Okay.
was something I was trying to figure out last night, so thank you.
Yeah, it's very unusual. We in the past we've never done this. We've never done that. We never had to deal with it this way, but the manual specifies it that way. So I figured we'd go through it. And then in the lab, I have a little appendix that describes this too. Okay.
Professor, how did you get the 2.5 again when it was multiplied by 0.01?
Well, basically, I'm moving this 2 decimal places, right? When I multiply by 0.1.
Oh, okay. Oh, okay, gotcha.
I mean, these other digits, because I'm finding the uncertainty, basically the least precise digit. So keeping these numbers is not going to be important. Okay. Okay, so that's how you're going to determine this uncertainty, this uncertainty, this uncertainty, this uncertainty, that one, and that one from your measurements. Okay, same with all these. So all the uncertainties in all these measurements, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The uncertainty of those 10 measurements basically come from your meter. Okay, look at the manual. So it's going to depend on what scale you're on and what the value is. Okay, because they're expressed as a percentage. And so you have to figure all them out. And so when you report your values, you're not only going to report these values, but also the uncertainties. Okay, so in table 1, and if you look at the heading, it wants you to report the values of the resistors and the values of the uncertainties. And by the way, it says kilo ohms for the resistance. You can change that to ohms if you want. You're not obligated to keep it to kilo ohms. Same thing with the current. If you want to keep it in amps, you're not obligated to keep it in milliamps. Okay? You just got to change the column heading, though. Otherwise, you're going to have results that look weird. And again, for this part, you have questions to answer. And in some of those questions, it's going to have you actually sum the voltage drops in a loop. It wants you to verify Kirchhoff's loop rule, too. And when you do that, you also got to calculate the uncertainty in that summation, because it says, do your results agree with Kirchhoff's voltage rule, or Kirchhoff voltage law? In other words, if the sum of the voltages equals 0, theoretically, does your summation agree with it within experimental uncertainty? So if you if you sum the voltages, or some of the voltage drops, and you get like 0.3 plus or minus 0.1 volts, then this doesn't agree with Kirchhoff's voltage law. But if you got something like this, then that agrees with Kirchhoff's voltage law. Yeah, expect to have values like this because you're trying to measure 0. The number 0 is very hard to measure. Okay. Well, it's one thing I learned in graduate school and as a postdoc working in the lab. Measuring 0 is hard to do, so expect 100% uncertainty when you're measuring 0. Okay, so make sure you do that uncertainty calculation in the questions. So there's a lot of air propagation. And you guys know how to calculate the uncertainty when you're adding two numbers, right?
I have to go back to my notes from last semester.
Okay. Just a quick reminder, because people will do the summation wrong for some reason. If I sub s is equal to I1 plus I2, then delta I sub s is equal to square root of you always use this prescription, right? We always take the partial derivatives. And this ends up being because you take the derivative of this with respect to I1, you just get 1. Okay. And then you also have a bunch of them where you have a quotient. So show your work. I mean, so I don't want you to show your work for every single calculation because your lab report will be tremendously long. Okay? If you're doing the same calculation over and over again, just show me one sample. But for each table, though, show me one sample. So if you're calculating, you're going to calculate this twice in part 1. Just do it once, right? Because you're going to calculate isobest twice. Just show your work for one of them. Okay, you're going to calculate I1, or you're going to calculate I 4 times. I just need you to show me this once, okay? Because the other 3 are going to be the same calculation, just different numbers. That makes sense? But then when you go to table 2, I want you to show the same calculation again. So for each table that you're filling out, if you're doing a repetitive calculation, just show that calculation once. I don't want to see it. Otherwise, your lab is going to be really long. Questions? Okay, so the other lab I want to talk about, and so this is due on November 5th. So there's a lot of calculations on this lab. The measurements are easy. I mean, I show you what the circuit looks like. The measurements are actually pretty easy. And you can tell right away if your results are bad or not, because if they don't obey Kirchhoff's current rule, then you did something wrong. And I showed you the circuit, what the circuit looks like. So the project you'll be doing really from between now and December 3rd, and most people are going to get started late, is you're going to build an electric motor. Here's an example of one that a student built a long time ago. This one had the Halloween theme to it. Okay, and so generally, especially when this course is on campus, students have a lot of fun with this, and they get competitive, etc. So you're going to build this motor in your lab kit. You have a motor kit. With everything you need to build a motor. Okay. You also have instructions. So you have instructions on how to build it. So the motor has 3 important components. Let me show you the built one. Okay, the important components are the commutator, which is where you make the connections. The brushes, I'm sorry, the commutator is this guy. The brushes is this guy. Let me turn it around. Okay. These are the brushes, these wires that make contact with this conductor. This is called the commutator, and it's kind of messed up over the years. This was made in 1999, and this was for a physics 110 class. And this is the armature. The armature is the part of the motor that transfers energy to the surroundings. So this thing spins, and you connect something to it, and it makes whatever's external to it spin. This thing converts electrical energy into mechanical energy. So you're going to use some nails, and really the nails and the wire are used to create magnets. So this U-shape set of nails with the wire wrapped around it really creates a magnetic field. And notice how nicely the wire's wrapped down here. Okay, notice how nicely the wire's wrapped. That's important. And then you're going to wrap wire around several nails to form the armature. This is the armature. This is the part that's going to transfer electrical energy, or convert the electrical energy into mechanical energy to the outside world. Okay, this will be the part that spins. And we'll talk about torque due to magnetic field, etc. Probably in a week, or maybe a little bit more than a week. So I'll say more about this motor. So your goal is to build this motor. Okay? But I mean, for you folks, you folks are going to be engineers. I put some stipulations on it. Okay. And you notice I gave you 2 batteries to power this motor, 2 D-cell batteries. If you can get your motor to run on 2 D-cell batteries, you'll get a high score for the motor. So the motor lab is going to be graded in 2 ways. Okay? You're going to be graded on the last page. The last page or the last... Hold on, let me get my printout. Yeah, so you'll be graded on answers to 5 questions on last page. So this is 10 points. And then you're going to be graded on the motor. And this is worth 30 points. So for a total of 40 points. If you can get your motor to run on 2 D-cell batteries and the armature and the commutator are connected in series, you're going to get 30 points on that. Okay? And then usually these questions, most people get full credit. So you're going to get, you'll get an A on the lab. And yeah, you can get this to work on 2 D-cell batteries. And the one thing that's been disappointing since we've been online is that you should be able to also get the motor to run on 1 D-cell battery. No one actually tries that anymore. When we have the lab on campus, students get competitive and they try to beat each other out whose motor runs on the lowest voltage. But online, it's not like that. Okay, so this is an individualized lab. You're going to build your own motor. And your goal is to have it run on 3 volts, 2 D-cell batteries. Now in the lab it says create a video showing that the motor works. So you want to create a video showing that the motor works. You want to show the wiring so I can tell everything's hooked up in series, and I got to see you in it too. Okay. You can vary the motor too. I mean, here's a variation of it. Although this one was too heavy and ran at 5 volts. We've had motors run at less than 1 volt. I think the record's like 0.8 volts. This one ran at 2 volts. This is another variation. So you can vary a little bit. Some people you actually put bearings in it. So the goal is to have fun on this lab. I mean, especially the folks who are engineers, they usually have fun on this lab, but it works better. People have more fun when we're on campus. So it does say you can create a video to show that the motor works. You can also demonstrate the motor in person. You don't have to make the video. You can come to campus and demonstrate to us that the motor works at a particular voltage. And then what we'll do is we'll sign your motor and write down on the motor what voltage it runs at. Okay. The one huge advantage of coming to campus and testing your motor is because we have much better equipment probably to improve your motor on campus than you have at home probably. If you're trying to improve your motor or test your motor at home to figure out what you can do to make it work better, you're probably not going to have the equipment at home. But if you're on campus, we have very robust power supplies that will allow you to test your motors. We have meters that allow you to test your motors. We have all kind of equipment that allow you to test your motors, and you can get it probably to run at a fairly low voltage. Okay, so you might want to take advantage of that. So after the 29th, all the labs will be in person, and so you can come to campus. I'll have in the lab the equipment for you to play with or use so that you can improve your motor. And then when you're ready to test it, you can test it in person. You don't have to make a video. Okay, I can test it, Tyler can test it, any faculty member who's here can test your motor. All they're going to do is sign, what they'll do is they'll sign the last page. Okay, on the last page, and I printed it, mine out small. It asks, oops. The last page has someone signing it and verifying what the voltage is. And it's got to spin on its own. It doesn't have to start by itself. If you need to give it a kick to get it started, that's fine. Okay? But once you give it a kick, it should keep going. All right? These are not like, you know, high quality motors we're building. Do you have any questions on this? Okay. So when we get to chapter 29 and I talk about torque on loops and magnetic fields, I'm going to say some more about the electric motor. I'll spend a little bit more time discussing the motor, but I want to present this now to tell you you can get started. You have the instructions in here and in the lab on how to build a motor. You have electrical tape. You have all the nails you need. If you need more nails, come and ask us. The magnet wire is very expensive. It's copper wire. Okay, so please be careful with it. Don't wait till the last minute to build this because it's not going to go well. Because one of the things you have to do is you got to make it work. Okay, you have to make this thing work, and you want it to work well. So if you're working on it the last minute, it's not going to go well. You can probably build a motor while you're sitting in front of the TV, you know, wrapping wire, etc. You can do that probably when you're sitting in front of the TV. But if you're going to try to make improvements to it, you're going to need some equipment to test it. That you cannot do in front of TV. You can't troubleshoot it. Okay, building it is pretty easy, but troubleshooting it is going to take some work. And one of the things about building a good motor is to make sure your wrapping is you do a good job wrapping things, because if you do a bad job, it won't work very well. Okay. So this one was for a Physics 110 class, the Halloween one. But so I just needed to see it work for that class. But you guys are engineering majors, I put more stipulations on it. So you can see the wiring here is, after like 20 years, has gotten kind of messed up. Okay. When you look at the wiring down here, it's not so great. Okay, and so this, although this thing still ran at 2 volts. Okay. When we do it in person, by the way, to get the full 30 points, you have to run it on 2 volts. Okay, so you have a little bit more leeway because this course is kind of online, and so I'm letting you run it up to. I'm considering the full 30 points for a 3-volt motor. Okay, that'd be cool if you can get it to run on 1 D-cell battery. And the other thing too is if you need more. If you're doing this at home and it doesn't work on 2 D-cell batteries, you have to buy some more D-cells. But if you come to campus, we have power supplies that run at high current. Okay. By the way, one of the things about these copper coil is that it's enameled, so it has a coating on it, but you need to sand down the ends to get the coating off. Otherwise, you won't be able to make electrical connections. Okay, and you don't want to run a high current for a long period of time, because then you might melt the enamel, and then your motor's ruined. Okay. All right. Well, I'm glad you say challenge accepted. It makes it more fun when the engineers are. Or the engineering students are kind of like competing with each other, trying to get trying to see who gets the motor, who can make the motor that runs at the lowest voltage. Questions?
No, but I'm looking forward to this one.
Okay, I'm glad. That's good. That's good. It's been different the last year because we were completely online. The dynamics, the class dynamics is different, and so you don't get that competitive nature to come out, and people just get the task done and that's it. But I think hopefully giving you a good opportunity to work on campus on some of the on your motors will help you to make will stimulate you to build a motor that works as best as possible. And I know some of the folks who are not engineering majors, this lab is not as fun for them, but for the engineering majors, it's a lot of fun for them. All right, so that's all I have to say. If you don't have anything to ask, have a nice weekend.
Do you have any tips on how the motor might be able to run better on a lower voltage? You don't have to give it. I don't want you to give it anyway. I was wondering if you have any tips.
I do, and I think that as you work on the motor, I mean, number one is the wiring has to be, I'll say this, the wiring has to be done well. You have to minimize the moment of inertia of this part that's going to spin the armature. Because if you have a mess, which happens with some students, then your moment of inertia is going to be higher, right? So you want to make sure that this is a balanced armature. Watch the friction. And then the other big one, and this is probably the biggest issue, is good contacts. Now some students will actually buy foil. I don't know if you can see it. Copper foil to make your electrical contacts. Okay? You can probably go to Home Depot or whatever. We've given you just the wire itself to make the contacts. And so I think, let me see. This one's gone bad, but this student just used the wire that's provided to make the contacts. Doesn't work as well. So having consistent contact as the armature rotates is a key to making it run at a lower voltage. Because if it stops as it's rotating, if it loses contact as it rotates, you're going to need a higher voltage to keep it spinning. Okay, so those are the big ones. And there's on the discussion board, I think I copied last semester's discussion board. I got to double check. I also have in there some tips and some videos. So check the discussion board. If it's not, I'll have to check if it's not there, but I copied the class from last semester, so it should be there. Okay? All right, so I'll stop here. Oh yeah, and ask your questions about how to make the motor run on the discussion board, because everyone's going to have similar questions. All right, you all have a good weekend.
Hey, so Professor.
Thank you, Professor.
Thank you.
You're welcome.
How long will you be at school today?
I'll be on campus till about, well, my class ends at 3. My last class ends at 3:30. So if no one's here at 4, then I will leave at 4. But if people are here at 4, I'll leave at 5.
All right, thank you, Professor.
Sure. Have a good weekend.